Location-aware navigation of a wheelchair in public spaces. A simulation study using Coppelia Sim.
When it comes to the problem statement of our project, we identify that wheelchair-bound people do not always have access to methods of independent mobility in public places such as shopping malls, supermarkets, and public libraries. So this reduces the quality of life of these people as well. The user has to be navigated in these public environments safely without collision, considering both static and dynamic obstacles. Also, the quality of this system can be improved if it is possible to provide data on the surrounded environment. So, this project focuses on developing a suitable location-aware navigation system for a wheelchair. Under the scope of the project, an urban shopping mall environment has considered as the simulation environment. Also, we define some limitations to simplify the problem. The target environment is for the system to interact with the common spaces of the shopping mall, and the individual shops in the shopping mall has not been considered. When it comes to the dynamic obstacle detection while navigating in the environment, we only consider one dynamic obstacle at a time. Objectives of the project. First objective of the project is to design a shopping mall-inspired simulation environment with both static and dynamic obstacles. Development of a simulation model of a wheelchair with the user interface can be considered as another one. The next objective is to develop a suitable path calculation algorithm to calculate the optimal collision-free path to reach a desired location while handling static and dynamic obstacles. Final objective is to develop a location awareness framework to be used in an enclosed public environment.
When it comes to wheelchair navigation, there were two main considerations. The first one was giving the opportunity to the user to click a button on the user interface and request the wheelchair to go towards a desired goal. The second thing was changing the goal position while navigating. Here in the screen, you can see that when the user clicks on a button on the user interface, the wheelchair will be starting to go towards the desired location by generating a path that connects the desired location and the wheelchair's current location. Here in this simulation, we will be showing you how the user is able to click on a button on the user interface and change the desired location while traveling towards the previously desired location. This is done by simply clicking on a button on the user interface, and you can see that when the user clicks on the button and changes the goal position, the wheelchair will be generating a new path and will be start moving towards the new location. Change in the final goal position or the final shop that the user wants to go can be done as many times as the user desires. So in this simulation, you can see that the user changes the final goal position or the final shop location 2 times while traveling towards the goal.
Environment mapping is done using occupancy grid mapping technique, and 2D LiDAR sensor data has used as input to this system. Probability of these cells represents whether the area is occupied or not by static obstacles, and output will be an array of ones and zeros where 1 represents occupied cells and 0 represents free cells. When performing dynamic obstacle avoidance, this occupancy grid map is used to identify the dynamic obstacles from static obstacles.
We have identified that the wheelchair can see a dynamic obstacle in 3 different ways. Hence, we have prepared simulations covering all 3 scenarios. In this simulation, you can see how the wheelchair reacts when a dynamic obstacle is coming towards it. As you can see here, even if the wheelchair detected a dynamic obstacle, it didn't stop. It kept moving towards the goal. The reason behind that is by using relative velocity, the wheelchair calculates the relative velocity of the dynamic obstacle with respect to it and decides that the dynamic obstacle will not hit it when it's moving. This is another simulation that shows how the wheelchair will react when a dynamic obstacle is coming towards it. But this is different from the previously showed one, because here the wheelchair stops when it detects a dynamic obstacle because it calculates the relative velocity and come to the conclusion that the dynamic obstacle will definitely collide with it. Then the wheelchair will be staying at the same place until the dynamic obstacle moves away from it and then starts navigating again towards the previously desired goal. This simulation shows the wheelchair's capability to identify and avoid obstacles that are not moving towards it nor moving away from it, but moving very close to it. In this simulation, we will be showing you how the wheelchair reacts when it detects a dynamic obstacle that is moving away from it. As you can see, the wheelchair didn't stop even if it detected a dynamic obstacle. Here in our study, we always assume that the wheelchair velocity is lesser than the dynamic obstacle's velocity. The main reason behind that is the main dynamic obstacle that is considered here are people.
Here we can see the wheelchair in the environment and how it provides the user with information about its surrounding. Note that in the current location, the shops to the right of the wheelchair are the shops A, B and C, and to the left of the wheelchair are shops R, S and T. While the wheelchair is moving, it takes photos approximately every 3 seconds and uses that image to predict the closest shops.